Now, we said imaginary numbers we can't place on the number line, and that is true. But we can still visualize the numbers by using a diagram, what's known as the Argand diagram, named after someone whose surname I'm sure was probably. Right, so we call it an Argand diagram. Now the amazing thing is, you've already seen the Argand diagram and you've been using it for a long time now, and you just didn't know it. Here it is. Oh, that's amazing. Okay? Now, of course, it's what we used to see as the number plane, but now we think of it as two things. Yes, it's a number plane, but now we think of it as an Argand diagram, where instead of having an x-axis and a y-axis, we have a real axis and an imaginary axis. Okay? So all our real numbers, so the real axis, so that's why that's horizontal, is like our number line. There's our number line. But now, going through the middle of it, vertically, is the imaginary number line. So all the pure imaginary numbers would lie on that number line. Those that are mixtures will lie in the space in between. So you don't really realise it, but as you're walking around, it's like the ground is your number line. You're quite comfortable with that. But all around you are these imaginary numbers. Okay? So how do we do it? Just like coordinate geometry. If I wanted to plot a equals 2, it's no different than saying put 2 on the number line. Oh, there it is. Amazing. And if I wanted to do a pure imaginary one, now I just use the other axis, minus 3i. There it is, down there. But what if it's a mixture? Just like plotting coordinates. The x value is -2, the y value is 1. So that's exactly where I put it, -2, 1. There's where we place that on the Argand diagram. So 4 minus I would have coordinates 4 minus 1. So there's D. This point E, look what happens here. And this is the beautiful thing. We start seeing lovely patterns when we think of it as a diagram rather than just these abstract numbers that are imaginary. 4 plus I, if I plot that one, there it is. But what's significant about that? These two numbers are conjugates. But what does it mean? Conjugates will always be reflected in the x-axis because their real part's going to be the same. So they're always going to have the same x value. But the imaginary part changes sign. So one will be above the axis, one will be below axis. So we'll always find conjugates reflected in the axis like that. What if I took the negative of a complex number? So the negative of D now, I'll get minus 4 plus I. Now what's the significance there as far as location goes? If you think of it two ways, you could think of it as straight through the origin. If I drew a line through the origin, and it'll be symmetric through the origin, if you imagine that. Or another way of thinking it is, if I got that number and rotated 180 degrees, just like we do with odd functions, that will create the negative of the number. So D and F, or negatives, will always be just like on the number line, because if you think about it, that's what, where do you put 4 and -4 on the number line? They're equal sides opposite of 0. Still true. They're equal sides on a line through 0, just now in space. Multiplication by I becomes quite important in some of the problems we look at. Look what happens when we multiply by I. The real part becomes the imaginary part, so plus 4i, and the imaginary part becomes the root part. So when we plot it, there it is up there. Now what is the significance in its location compared to D? And you might not immediately see it. Think of this idea of rotation rather than reflection through 0, and you'll see it. It's rotated as well, but it's only 90 degrees. Every multiplication by I rotates the point 90 degrees. Multiply by I, 90 degrees. Multiply by I again, in other words, you've multiplied by I squared, which is -1, you've rotated 180 degrees. Multiply by I cubed, you've rotated 270 degrees, because now you're multiplying by -I, if you like. Rotate a fourth time, I to the power of 4, which is equal to +1, you're back where you started from. Okay? But the other lovely thing is, Every number has a unique position. Every point on that could only be one possible number. So no two numbers could have the same point. So we've got a lovely way we can plot the infinite number of different complex numbers or imaginary numbers, but we can see it visually and we get some wonderful pictures. So now locus becomes really, really interesting because we can do it in terms of complex numbers. Right? Horizontal and vertical lines, they're probably one of the first things we drew when you did coordinate geometry. So let's do them. There's a horizontal line. But now instead of calling it y equals c, yes, if that's a number plane, yeah, that's its equation. But if I'm now looking at the Argand diagram, I'm saying, hey, all those imaginary numbers that form this line, what do they have in common? They all have the same imaginary part. And so its equation becomes the imaginary part of z is equal to c. So that's what the line has in common. That's its locus, if you like. And so a vertical line, similar sort of thing's going to happen, but all the things they have in common is the real part's the same. So yes, when it's a number line, a number plane, we'd call it x equals, but when we now talk about the Argand diagram, it's the real part of z equals k. Circles. Whoop. Now has this equation, remember? I said there's more significance to this x squared plus y squared. A circle would normally be x squared plus y squared equals the radius squared. But when I'm thinking of complex numbers, x squared plus y squared is a number times its conjugate. And so this now can have the equation z times z conjugate is equal to the radius squared. Find and describe these points. Whoa. It's still z times z conjugate, but something's happening. Let's see. We'll do it the long way so you can see what ends up happening. If I was to expand the whole thing out, what happens? Let's tidy it up a bit. A little bit of mass. Because I have no idea, I'm now going to, everywhere I see a z, substitute in. And so z times z conjugate, I know is x squared plus y squared. Z plus z conjugate is twice the real part, or 2x. Here I've got I times z times z conjugate, so I'll end up getting 2y. Basically, everywhere there's a z, I'm substituting in x plus iy. And I'll end up with this equation. Still not quite there. I can't quite tell what the circle is. Going to have to complete the square and so on. Okay, let's do that. Complete the square. That's what I end up with. X plus 4 squared plus y minus 1 all squared is equal to 49. Let's now go back to the original equation. 49 is still 49. Terrific. 4 and 1. Well, they were significant numbers here. So what ends up happening is, where is the centre of this circle? That's on the number plane. Where is it? On the Argand diagram. What point? What complex number? -4 plus I. Let's go back to the question. What is -4 plus I? Z minus Z conjugate. If I'd written that there, 4 plus I is the negative of what we just said. So it's a locus as a circle, -4 minus 1. So if we see this situation where it's Z plus a complex number, conjugate of Z plus the conjugate of that number, that's effectively what we're there. We know, hey, that's a circle. And its centre will be Z, same as when we normally have it, Z minus the centre. So this is Z minus -4 minus I. Now let's have a look at this one. Don't recognise it straight away. So if I don't recognise it straight away, I want to get x and y. So I might be able to think of, well, what does this look like on a number plane? And then I'll know what the shape is. So if I don't recognise it, I replace z with x plus iy. And then I'll get x and y's in there, and I can come up with something. So let's play with it a bit before I sub in. If I multiply everything by z conjugate, it makes life a little bit easier. So I now know, because I've got z plus z conjugate, twice the real part, 2x, equal to z times z conjugate, x squared plus y squared. Looks like I've got another circle. Let's hope I did this one right. X squared minus 2x, complete the square. There's my circle. So Locus's circle, centre 1 naught, radius 1 unit. There it is. Whoop. Draw a picture. Now, here's the interesting thing. That actually is not the final answer. There is a problem. There is a problem. Because what I'm saying is, all the points on this circle are the solutions to that original equation. Well, that's not true. Not true at all. Where's my problem? Now, at the origin, I still have that problem of I can't divide by 0. The origin is 0, 0. So 0 real plus 0 imaginary, it's still the number 0. And so if I sub into the original one, I'm going to say, well, 1 over 0 plus 1 over the conjugate of 0, which is also 0. I can't do that. So we have to exclude that point. So actually, if I was to draw the diagram, I'd have a complete circle, but then I'd draw a circle on the origin to indicate not included. Not included. Why does that happen? Because you see, I've changed the equation. So whenever you do that, you always go into, hang on, what was the original question? Does it solve the original question? Is there any problems there? Okay.